or it can also, or there can also be a phase shift keying. So these are shown here as A, B, and C. So the first one, this is what is the amplitude shift keying. I believe you are already familiar with this. And the second one is the frequency shift keying, where the depending on what is the bit to be transmitted. In the first case, the amplitude is different. In the second case, the frequency is different. And in the third case, the phase is different. I believe you are already familiar with this. So, uh, there are advances in the frequency shift keying and phase shift keying, and people are always trying to improve the reliability of the coherent systems. The diagram is shown. So this is a simple coherent receiver model. Yeah. So uh, the electromagnetic fields which are coming from the two lasers, these can be represented by cosine functions. Okay. So this is actually not an exact representation but a approximation, and depending on these cosine functions, a phase relationship mm, can be represented by this expression. Phi is phi s minus phi l. Phi s refers to the phase of the source or the transmitted signal, and phi l refers to the phase of the local oscillator signal. Okay, and this is what is a representation of uh, what was transmitted, and this is the what is being emitted by the local oscillator. So um, so there's an angle phi t which represents the phase relationship between the two fields. Uh, and it also contains the information which was transmitted. In case of ASK, phi t is constant, and this can be written as phi. So phi t contains the uh, information contained which was transmitted in case of FSK or PSK. And the information is contained in what is the amplitude ES in case of ASK. For heterodyne detection, the local oscillator frequency is offset from the incoming signal frequency by an intermediate frequency, such that you have this relationship among the different frequency components. And uh, this intermediate frequency is usually in the radio frequency region, uh, and it can be of the order of some tens or hundreds of megahertz. So when this intermediate frequency is of this order, then we can use the standard techniques which are available uh, in RF detection. And when we are considering when when we are considering the homodyne detection, in that case there is no offset between omega s and omega l, and that would mean that omega f is 0. So uh, the combined signal would therefore come directly in the baseband. So what this means is, so when you're doing a homodyne detection, then uh, you'll get the transmitted information directly at this point, and it can just be amplified to get the output data. You do not need a demodulator after that. So there's a catch with homodyne detection. The two wavefronts which are coming in at the detector, one from the transmitted signal and the one from the local oscillator. These must be perfectly matched for ideal coherent detection. Otherwise, there would be always some uh, noise which would arise out of this. So this is a basic coherent receiver model wherein you have both the local oscillator and the transmitted signal coming in at the detector. So these are the modulation formats which can be deployed in fiber optic communication. So amplitude shift keying is the most basic, and it is the simplest approach, which is used for fiber optic communication. There is a problem because the laser uh, has a difficulty in maintaining a stable output frequency. Whenever, if there is a problem with the laser controller, then the output uh, the output may jump, or the what is termed as mode hopping. So mode hopping can happen, but of course with very highly reliable laser drivers, this is not a very big problem. So uh, to have this amplitude shift keying, it's possible to have direct modulation, but direct modulation of a semiconductor laser usually does not give very high data rates. The modulation capability by using the direct modulation is limited to uh, the order of some Mbps. So that is the reason the Mach Zehnder interferometer is commonly employed to go for the indirect modulation or external modulation. Uh, yeah, but even this external modulators have this drawback of consuming a lot of power. Half of the transmitted power is consumed by the modulator itself. Uh, it's possible to also have non-synchronous or asynchronous detection with the amplitude shift keying, and if this is employed, then um, the injection laser phase stability need not be that rigidly maintained. So if the laser wavelength is yeah, if the laser wavelength is drifting, then it does not cause a very serious issue. So this modulation scheme can be used uh, with laser sources exhibiting line widths comparable with the bit transmission rate. So um, in practice, the line width is in the range of 10 to 15% of bit rate for ASK heterodyne detection. So, uh, but some use even lower line widths. So, if this asynchronous heterodyne detection is implemented, then the line width need not be all that low. Typical DFB lasers can be used, which have line widths of the order of some 1 nanometer or so. So if we are talking about 10 to 50%, then it refers to uh, line widths of the order of zero point 0.1 nanometer or so, zero point 0.1 to zero point 0.5 nanometers. That is what is usually needed for ASK heterodyne detection. But for asynchronous heterodyne detection, it's possible to have line widths of the order of even 1 nanometer. Next modulation format which can be used is the frequency shift keying. Uh, this can be used in the form of directly with a directly modulated semiconductor laser, meaning if you change the frequency of the uh, input, then accordingly the output frequency can change, meaning a mode or it can result in a different mode being transmitted. So when a different mode is transmitted, there's a small shift in wavelength. So this can give rise to frequency shift keying. Uh, so um, so it's possible to achieve this frequency shift keying without an external modulator, and if an external modulator is not used, then you're able to limit the power loss of the external. You're removing the power loss because of the external modulator, and hence you can launch higher powers onto the fiber. And because of this, the transmitter configuration can also be much smaller. The size of the transmitter can be smaller. So, of course, temperature plays a part. The temperature of the laser uh, defines which mode is actually emitted by the laser, and if there is a change in temperature of the laser, then the mode which is being emitted that can change and give rise to a different frequency. So it's possible that you can have errors because of this. And the laser line width requirements for the FSK heterodyne asynchronous detection are similar to those of ASK asynchronous detection, and it can be 10 to 50% of the transmission bit rate. Uh, so this is more or less uh, successful, particularly at low bit rates. So low bit rates here refers to something around 1 Gbps. So frequency shift keying can also be done with external modulation, and this can be implemented by using electro-optic approach or acousto-optic approach. So if you're using a Bragg cell, then traveling acoustic waves in a crystal can diffract and change the frequency of the optical signal. So I believe you're already familiar with what is the Bragg diffraction, right? Must have gone through this in physics. So the same Bragg diffraction, the effect which is observed in Bragg diffraction can be used to have frequency shift key. So this is different types of um, modulation, or how the modulator or how modulation can be implemented for FSK and PSK. So coming to phase shift keying, the optical phase modulation can be achieved by DC modulation of a semiconductor laser, into which external coherent laser light is injected. So this is so if there is perfect tuning between the modulating signal frequency and the laser frequency, then the output signal phase relative to the modulating signal phase is zero. So if there is a relative phase change of pi by 2 between the two, meaning the laser frequency and the modulated light frequency, then you have a phase shifted signal. Uh, this technique has the effect of reducing the line width of the injection lock laser to that of the injected signal device, uh, because the phase needs to be perfectly matched. So the line width also becomes less. Uh, the phase shift keying is simple to implement by using external modulators. Uh, and actually, a phase shift, the phase shift is the basic technique which is used to implement even amplitude shift key. So the same lithium niobate platform is usually used to get the phase shift and the amplitude shifting also. If I remember, I had given you a brief I think I had spent a few minutes on how electro-optic modulation is achieved. So that electro-optic modulator, which gives amplitude shift keying, also uses phase shift to implement the amplitude shift keying. So if one has to use phase shift keying, a part of that amplitude shift keying device can be used to get the phase shift keying. Polarization shift keying is not all that popular, but people are trying to work out models of using this additional dimension which can enhance the uh, data carrying capability of the optical fiber. So, a standard fiber, usually it is observed that two different polarizations are supported in a single mode optical fiber. So, the two different polarizations can be used separately to carry either a 0 or a 1 bit. But uh, even though the optical fiber supports two polarizations, the two polarizations along the length are very interchangeable. So that is the reason this is not commonly employed. So it's difficult to have the polarization of the input maintained throughout the length of the fiber. So for that, there is a different class of fibers, as I had mentioned earlier, which is known as polarization maintaining fibers. So, uh, but polarization is useful uh, because it can be used to enhance the data transmission capability of the optical fiber. So this can be an added dimension which can be used, and if this can be implemented, then the data rates can double. If this can be implemented along with one of the standard uh, transmission techniques, then the data transmission rate can be doubled. So that is the reason this is being uh, pursued. Demodulation schemes. We have the heterodyne and homodyne detection. Um, so this is about um, the detection. Part A, the top part is the heterodyne receiver, wherein the wavelength of the local oscillator is different from what is coming in from the transmitted source, and the intermediate frequency is usually this is now in the uh, radio frequency range, and the standard demodulation techniques which are employed in the radio frequency range can be employed here to get back the baseband signal, and this can be amplified and filtered to have the data. So the local oscillator needs this automatic frequency control to have a stable output frequency. So if there is any uh, noise because of wavelength shift of the local oscillator, then that is corrected by this automatic frequency controller, that is detected by the automatic frequency controller, and it sends a corrective signal to the local oscillator. So this usually reduces the current or increases the current which is being transmitted to the local laser oscillator. So here it's a similar thing, except uh, here the local oscillator is also detecting what is the wavelength which is coming in, and accordingly it sends uh, the same wavelength to the detector. So the rest of the blocks are understandable. So this automatic frequency control provides frequency stabilization, and any variant detection uh, which is based on homodyne detection. Um, but in which the local oscillator is not phase locked to the incoming signal. So what you see here, this input signal part which is going into this local oscillator, this uh, local oscillator gets the same phase this input, and accordingly this output is having the same phase as this incoming signal. So that is the reason this is also known as a phase locked loop, PLL. So if a phase locked loop is not present in a detector, then you can say that is a kind of heterodyne detection also. So uh, in both heterodyne and homodyne detection, both use a local oscillator, and frequency modulated noise which results from source laser causes signal to noise ratio degradation in the receivers. It can be possible for any of the modulation techniques, and this determines what is the lower limit of bit error rate performance. So uh, so in case of heterodyne synchronous detection, the phase lock loop which is employed is in the electrical domain. So this is a block diagram of carrier recovery which is used in coherent optical PSK receivers. The first one is a squaring loop, and the second one is a Costas loop. So, uh, so these are what are known as phase lock loops to get the phase locking at the intermediate frequencies. Uh, So this is about phase shift key recovery of phase shift keyed signal, a squaring loop as is indicated at this top part. This can be used to detect the phase changes and recovery of the signal. Of heterodyne asynchronous detection, uh, you can have ASK and FSK. Both can be demodulated using asynchronous detection techniques. And in asynchronous techniques, the laser line width and phase stability need not be constant. So this is a block diagram to have asynchronous ASK detection. So um, you have a detector. It compares the two inputs and it sends the signal to an amplifier, and then a band pass filter uh, is used to get the desired frequency range, and then a demodulator is implemented. A demodulator is used to get the desired data format, and then a low pass filter to get the data directly. And this is a FSK dual filter receiver. So this received signal is split into two parts, and the two different frequencies are captured, are transmitted, or are sent through by the bandpass filters. So the envelope detector says if this particular frequency is present or not, and accordingly you have the data at the output. So depending on which frequency is present, accordingly the output is obtained. So this is for a DPSK signal. DPSK refers to differential phase shift keying. So in case of a differential phase shift keying, uh, after the detector, a band pass filter is used, and then a 1 bit delay is employed, and then it is added with the with this same signal. Okay, and then this added signal is passed through a low pass filter to get the output data. So these are different demodulation techniques for ASK, FSK, and PSK. Different asynchronous demodulation techniques. In case of um, uh, so homodyne detection has this advantage that higher power can be transmitted. The receiver bandwidth can also be higher. So heterodyne detection needs much higher bandwidth than what is necessary for homodyne detection. But there are problems associated with homodyne detection. using independent source and local oscillator. Uh, and this phase locking is a necessary part, and it is not that simple to implement. The um, modulated signal is of very low levels. So this is the spectrum which is used in case of homodyne detection and heterodyne detection, and you can see the bandwidth which is consumed by a heterodyne receiver is twice of what we have for a homodyne receiver. So uh, in homodyne demodulation strategies, there's the use of a pilot carrier, which can improve the reliability of the system, or it can also be an optical phase lock loop. So any of these two can be used to get the desired data transmission capability. Okay, so this is about today's class. If you have any questions, if not, you all can leave. I think it's already time for your next class.
Thank you, sir.